Hello, it's Paul with an R script to illustrate the intermediate value theorem, its proof, and some of its corollaries. Let's start with the proof. I've specialized very slightly so that my illustration will match the proof in ROS exactly. I've chosen two real numbers, a and b, with a less than b, and a and b are both located in some interval I on which our function f is continuous, and I have made f of a be less than some value y, while f of b is greater than y. All that really matters is that one of the values be larger and the other be smaller. So the specialization is I've made the smaller value be at a, the larger value be at b. And the conclusion of the theorem is that somewhere in the open interval from a to b is a value x for which f of x equals y. There may be more than one such value, and we are going to be finding the largest of these values. Let's set up our margins to maximize space, set up a couple of axes, and define a rather interesting function that wiggles. There it is. Being a polynomial, it's continuous, and in particular it's continuous on the interval from 0 to 4. I've chosen two values, a and b, that lie in that interval, and marked them off with vertical blue lines. So, at the lower left you have a and f of a. At the upper right you have b and f of b, and in green I've plotted my target value. You can see that f of a is less than y, f of b is greater than y. So we're going to illustrate the proof that there's at least one x in that interval. It's obvious here there are in fact three of them, such that f of x equals y. So here's the first step. I'm going to construct a subset of the interval a to b. This is a subset in the domain for which f of x is less than y. I will do this by using the uniroot function. Of course, the uniroot function only works because of the intermediate value theorem. The intermediate value theorem guarantees that we can find these solutions. So I find the three intersections of the graph with the green line at 1.12, 1.79, and 3.08. And now I will color in on the horizontal axis the portion of that axis that corresponds to the set S. A little bit running from A to the first point of intersection, and then another segment running between the second and third places where the graph crosses the green line. So the set S, I repeat, is a subset of the domain. It corresponds to the red part of the horizontal axis. The supremum of this set S is at 3.088. Now, we're using Ross's every sequence is good definition of continuity, so I will make a sequence in the domain that converges to x0 from below. What I'm going to do is take x0 and subtract off 1, 1/4, 1/9, and so on. None of these can possibly be an upper bound for S because the supremum is x0. So I will construct a sequence that's almost but not quite the same. I'm going to make sure that the values are all greater than 1.791, thereby guaranteeing that they're all inside the red set. I think in this particular case that would have been true anyway, but might as well play safe. So there is my sequence, and you can see the points start a little bit above 2 and quickly close in on x0 from below. Now I apply f to that sequence. Since f is a continuous function, every sequence is good. This sequence has to converge to f of x0. And because every x value in the set is in the red part of the domain where the function values are less than y, I'm going to get a sequence in the codomain for which every element of the sequence is less than my target value of 0.2. That means the limit of this sequence cannot possibly exceed my target value y. Now I will creep in from the other side. Construct a sequence of points, all of which are bigger than x0, making sure that none of them is larger than b. And there in cyan, I have a sequence of points, none of which is in the set S. And this sequence, again, converges to the supremum of the set S. I apply f to it. Since none of the points are in the set S, all the values in the codomain must be larger than y, and therefore the limit of that sequence, which has to be the limit f of x0, cannot be less than y. And now I've got it. F of x0 cannot be less than y. Earlier we found it couldn't be greater than y. What's left? It has to be equal to y, and we've proved the intermediate value theorem. Let's look at a couple of corollaries of this extremely useful theorem. Suppose we have a function that on some interval I is strictly increasing. Here is such a function on the interval marked off by the vertical blue lines. Notice this function is not strictly increasing on 0 to 3, but it is strictly increasing on 1 to 3. There's a target value, and the intermediate value theorem says there has to be a point in the interval for which that target value is achieved. Since the function is strictly increasing, there's only one such point, and therefore we know that on this restricted domain the function is not only surjective, the intermediate value theorem guarantees we'll hit our target, but it's injective. There's only one point in the domain for which we can hit it, and therefore we have a bijection between the domain and the codomain, or equivalently, there's an inverse function from the interval of the codomain between the red lines to the interval of the domain between the blue lines. This is the inverse function, and it's also strictly increasing. One more corollary. Suppose we've got a closed interval from a to b and a bounded continuous function on that interval. Saying that the function's bounded means that there is a supremum m, and what we're going to prove is that this supremum is actually a maximum. That is, it's not achieved just as a limit. There is a value in the domain with the property that when we apply f to that value, we get the supremum. And here's the construction that proves this result. I've set up a nice, wiggly, ambiguous function. So notice it's not at all obvious exactly what the maximum value is. It could be that this maximum is actually achieved in two different places. R conveniently has a function that finds the supremum. It's called optimize, and if I put $objective after it, the result that I store in M is the least upper bound of the values of the function on that interval. Now I'm going to construct a sequence in the codomain that converges to that supremum. I chose it to look rather nice. It's m minus 1 over n squared, just 15 values plotted. And I put green lines for those 15 different values. And now I'm going to construct a sequence in the domain. I'll need 15 values there. And I'll do these one at a time. I'm using uniroot to find the x values, and I'm doing it rather capriciously. Right there you can see for that second green line I had 4 different choices. I picked one of them rather arbitrarily. There's another one. There's another one. So bouncing around, we get a bunch of points in the domain. Now, the sequence in the codomain clearly converges to the supremum x. It's obvious from looking at the points and thinking about their horizontal coordinates that the sequence of x values doesn't converge. If you look at that sequence, it bounces all around, going back and forth between values that are less than 1 and values that are greater than 2. But Bolzano-Weierstrass comes to the rescue. It has a convergent subsequence, and all I have to do is look at the elements of that sequence where the value is less than 1.5. And if you look at that, we don't have enough so that convergence is obvious. But if you look at the points on the graph, it is highly plausible that that sequence converges to something. And the Bolzano-Weierstrass theorem guarantees that it converges. What does it converge to? It converges to that value x0. And since the function's continuous, every sequence is a good sequence. If the sequence in the domain converges to f0, the sequence in the codomain converges to the value m. So we have found a maximum. The maximum is the value x0 for which f of x0 is equal to m.